Hello everyone, this is group 9. We are discussing hierarchical clustering. My name is Sunil and I'll be talking about the introduction. So before we define what hierarchical clustering is, we need to define what clustering is. So clustering is grouping of the available data into different sets of groups so that the data in each group is similar to every other data, and each group is different from the other groups, like they have some clear distinction. Now, hierarchical clustering is a type of clustering in which each data is like grouped into set of other data so that they form clusters, and each cluster has some nested subclusters. So this is in contrast with the partitional clustering, where each, like, we split the data into separate clusters so that there is no overlapping between them. In hierarchical clustering, we represent the clustering in a tree format where each node is a cluster and its children are subclusters, and the leaf nodes are individual data points. Now there are different types of hierarchical clustering, such as agglomerative and divisive. So in agglomerative, we take two clusters and then we merge them, like, so that they are we the clusters that we select to merge are such a way that they have like closest proximity. So we need to define what proximity is between each cluster, and we repeat the process until we reach a single cluster. And when it comes to divisive clustering, we take the entire cluster, entire data, and then we split the cluster into different set of clusters, and then we select one of the cluster from that, and then we repeat the process. So in divisive method, we need to define how we select the best cluster to split. Now let's talk about the agglomerative approach. This is the algorithm for the agglomerative approach. So for that, first, if you don't already have the proximity matrix, we need to first compute it. So this depends on the type of data, and we define the proximity between every pair of clusters. Now we take two clusters so that they are close to each other, we merge them, and we repeat this process with another cluster, so that at the end we only have one cluster. So here steps 3, 4, 5 are repeated until only one cluster remains. So we represent hierarchical clustering in a tree-like structure called dendrogram. So here in dendrogram, uh, both the clusters and the subclusters relationship is represented. So for example, here we have P2 and P3 which are closest to each other, so we first merge them, and the resulting cluster is merged with P4, and that is merged with the P1. Now this is the algorithm for the divisive approach for hierarchical clustering. So here we take the entire data and then we split that into different clusters using another clustering method such as k-means. Now we need to select one best cluster among these clusters to repeat the process. So we split that selected cluster again using the flat clustering algorithm such as k-means, and we repeat this process until there's only until the clusters remaining have only one dataset in each of them.
Hi, my name is Saranya. I'll be talking about what is clustering and what are the different techniques involved in the clustering, why we need the hierarchical clustering, and the number of different values required for the hierarchical clustering, such as the number of cluster calculations and the distance between the cluster calculations, and how we compute those values, how to identify the dissimilarities between the clusters, and what are the real life applications of clustering algorithms. To start with, what is a cluster? Clustering techniques. Clustering is something which will help us to analyze the data, and it will also help us to group the data based on the different data traits. This will help us to achieve a deep and the very clear data analysis and results. So the different clustering techniques are the hierarchical clustering, partitional clustering, overlapping clustering, fuzzy clustering, complete clustering, partial clustering, k-means clustering, and the DB scan clustering. Different types of clusters would be well separated cluster, prototype based clusters, and the graph based clusters, density based clusters, and the shared property clusters. So, as we have these many clustering techniques, we are more focusing on the hierarchical clustering based on a project's topic. So, why do we need the hierarchical clustering? To know the reason behind this, um, let's initially consider the k-means clustering, where it will help us to analyze the data. But one major drawback with the k-means clustering would be it will expect us to predefine the number of nodes required for the data analysis for any given data set. So it is difficult for any user, to calculate the number of nodes or the clusters required for the data set in their hand. So, to overcome this challenge, the hierarchical clustering concept was introduced. How hierarchical clustering helps us to overcome this challenge is by introducing a concept called similar data grouping. So, in while implementing this concept of grouping the similar data, we can overcome the predefined number of nodes theory, which will help us to analyze the data in a better way. So, this hierarchical clustering can be implemented in two different types. One is the agglomerative approach, and the other one is the divisive approach. In the agglomerative approach, um, it follows a certain pattern where all the data set is considered as different nodes, and with these scattered nodes, we are going to group initially we'll be grouping certain nodes together based on certain criteria, and the different nodes based on the different criteria, and at the end we will have individual clusters for each and every node. This is how the agglomerative approach works. And in the divisive algorithm, all the nodes are considered within a single cluster, and the single cluster is then divided into multiple clusters. This is how the divisive algorithm works. So to implement these approaches, we require two different values. One value is the number of clusters required to implement these approaches, and the other approach is how to identify the similar clusters. To identify the similar clusters, we must calculate or compute a value called the distance between the clusters. So these are the two important values which needs to be computed to implement the hierarchical clustering. Um, the dendrogram technique will help us to calculate the number of clusters required to implement the algorithm, and whereas the proximity matrix will help us to calculate the distance between the cluster in the for the given data set. Uh, for the proximity matrix, we use a formula called the Euclidean formula. This is the formula which is used to calculate the distance between the nodes, where we consider the difference between the start node and the end node value and calculate the Euclidean formula. So here I've considered a student score as an example, and based on this student score as the data set, I've also explained how we arrive at the proximity matrix. So this is how we calculate the proximity matrix. This will help us to find the difference between the different clusters. Um, once we have calculated the distance between the clusters, we will be grouping the the less distance value together to form the clusters or grouping as said in the agglomerative hierarchical algorithms. Um, so once we have found a way on how to group the similar clusters, we should also know how to identify the dissimilar clusters. So there are certain techniques where we can, which are followed to identify the dissimilar clusters, which are nothing but the complete linkage clustering, single linkage clustering, average linkage clustering, centroid linkage clustering, and the Watts minimum variance methods. Among these different techniques used to identify the dissimilar clustering, let's see what are the approaches followed in the agglomerative and the divisive algorithms. For the agglomerative clustering algorithm, we use the complete linkage and the Watts method to calculate the dissimilarities between the clusters, and the divisive algorithm uses the average linkage method to identify the dissimilarities between the clusters. Using these techniques, we can use to identify the left out clusters apart from these similar clusters, and proceed accordingly from there. So these are the different techniques and the value calculations and the computations used while implementing the hierarchical clustering. Now let's see the real life applications of this hierarchical clustering models. One such, the popular method of hierarchical clustering implications in the real life is identifying the fake news, where we will have multiple data sources for the news. We will consider the words or the letters used in each of these news, and calculate the hit percentage of each and every word. If whatever word is used in multiple data sources or the news sources frequently, will be considered as a valid news, whereas the other words which have the lesser frequency or the occurrence percentage will be considered as a fake news. The second implication would be the spam filter, where we will get where in these days we are getting multiple spam emails. So to identify the spam or to implement the spam filter, an email is first analyzed for its header content and the sender informations, and based on these trained models or the of these algorithms, a spam email is judged and then moved to the spam folder. Marketing and the sales say every product will not be a great fit for all the customers. So the customers based on the interest and the traits are grouped together, and certain and the relevant products are marketed to those relevant groups, and this is how the hierarchical clustering will help in the marketing and the sales. And next comes the network traffic and identifying the fraudulential activities, where the fraud incidents based on a specific traits are grouped together and then marked as the fraudulence based on the activity patterns. And the data analysis and the football sports or any sports games, when the captain of the team will decide which player to hold in their team. So based on the characteristics and the performance levels of each player, the data can be grouped based on different categories, and a decision can be made at the end. So these are the different implications of the hierarchical clustering, and this is all about my PPT. Thank you.
Hi, this is Yogananda. Today we will be discussing about DBScan. So DBScan, it is also known as density-based spatial clustering of applications with noise. So it is an unsupervised machine learning technique which sometimes works better than k-means clustering and hierarchical clustering. So why we would use DBScan? So for example, now imagine we collected weight and height measurements from a bunch of people, and we plotted the people on a two-dimensional graph like this, where we have weight on x-axis, first dimension, and height on the y-axis, which is second dimension. By eye, we can see we have two different clusters, green and blue, which are densely populated. On the other hand, we can see these remote clusters, remote points, so which are known as outliers. So these are basically outliers. So by clustering, this data is pretty easy. However, because these clusters are nested, meaning we can see these clusters are nested. So however, because these clusters are nested, meaning the green cluster wraps around the blue cluster, so a relatively standard clustering method like k-means clustering might have difficulty identifying these two clusters. So what happens is that instead, because of the nestings, a simple clustering method might get something weird like this. So we can see here that this group of points are actually classified into blue color, but actually they belong to the green color. So this is what happens when we use a simple clustering algorithm like k-means. So we need a clustering algorithm that can handle this nested clusters. Also, we need so we can see that this is a two-dimensional graph, so which uses only weight and height data. But if we wanted to include another feature, which is a new feature like person's age, so we would have to add a third axis, and then our graph is three-dimensional. But if we have four or more features, we would need to draw four or more dimensional graph, and that's not possible. And if we can't draw and look at four or more dimensional graph, then we need a way to identify these nested clusters that we cannot see by eye. So the good news is that there are clustering algorithms that can identify nested clusters in high dimensions, and DBSCAN is one of them. So DBSCAN, it actually works like based on set of points. Let's think in a two-dimensional graph as seen before. So DBSCAN groups together points that are close to each other on a distance measurement. Usually we assume the Euclidean distance as a default one, and the minimum number of points, it also marks as the outliers. So as we have seen, there were some points which were considered to be remote. So this would be the outliers. So coming to pa parameters and classification. So the DBSCAN algorithm basically requires two parameters. So the first one is epsilon, so which specifies how close points should be to each other to be considered a part of cluster. It means that if the distance between 2 points is lower or equal to this value, which is the epsilon value, then those 2 points are considered neighbors. And next, coming to the other component, which is minimum points. So it says that the minimum number of points to form a dense region. For example, if we set the minimum points parameter as 5, then we need at least 5 points to form a dense region. So the classification of points in DBSCAN algorithm are core points, border points, and noise points. So let's understand all these components with the help of a figure. So coming to this figure, so let's consider some initial points as shown in the figure. So these are the points. Initially, we consider some epsilon value and some epsilon random value, and let's consider some minimum points value, which is 4. So it depends on the distance basically. So when coming to the first component, which is the epsilon, so suppose this is a point which has, suppose let's consider this point which is C. So this point actually has a radius as epsilon naught. So we will be this epsilon value is 3, let's assume, and we create a circular boundary across it in such a way. The next component is minimum points. So in this case, we have minimum points as 4. For suppose if we have 4 points like 1, 2, 3, 4 across this boundary, inside this circular boundary, we have 4 points. So in this case, we consider the point C to be a core point because it has got 4 points, which is the minimum points value 4. it has 4 points inside this circular boundary with the radius as epsilon value. So this point is considered to be a core point. So the next component, so let us consider a point A. So let us consider a point A. So it has a radius of epsilon, and let us assume the circular boundary across it. Okay, so this is the radius. For example, it does not satisfy the conditions which is 4 points. So this circular boundary doesn't have any 4 points, but it does have a core point inside this. So the condition is it doesn't have minimum points as 4, but it does have a core point inside the circular boundary. Then this point A is said to be a border point. Next, if we consider another point D, sorry for this, yeah, this is a point D, and let us assume it has a radius, so it has got the radius as epsilon value, and for this point D it has no it has no core point inside it, and it doesn't satisfy the condition minimum points for. So there are no point, it doesn't satisfy the condition for, which means that there are no 4 points inside this, and it has got no core point. So this would be, the point D would be considered as a noise point. So noise point is basically an outlier. So DBscan nicely handles this outliers. So which basically means that whenever DBscan discovers any noise points, so it will be considered as an outlier. It will never draw the circular boundary across it. It will skip that point and never treat it as a part of a cluster. But coming to the case of core and border points, it will be considered circular boundaries across it and treating it as a treating it as a cluster. So as you can see that, let us assume this circular path, circular boundary. So let us assume this is the point A. So it has got 4 points inside of this circle. So this point is said to be a core point. But for example, if we take this point, which is point D, if we take a specific radius for this and draw a circular path across it, we can see that there is only one core point inside this circular boundary, and it doesn't satisfy the minimum points condition. So this point would be said to be a border point. But coming to this case, if you see, this is a noise point. So it doesn't satisfy the condition of minimum points and doesn't have a core point inside it. So it is said to be border point. So next we can see that the DBscan algorithm. So it labels all points as core, border, and noise points, eliminates noise points, and put an edge between all core points that are within epsilon of each other. Make each group of connected core points into separate cluster. Assign each border point into one of the cluster of its associate core point. And coming to parameter estimation, so we see that epsilon value is chosen to be too small. It shouldn't be too small or too big. It should be based upon the distance of the data set. In general, we assume epsilon value to be preferable to be small. I mean, my points, it depends upon the dimension. There are usually better data with noise for more significant clusters. The minimum value for minimum point should be 3, but larger data set, larger the minimum points should be chosen. And next, what are the advantages and disadvantages? As we have seen, it is great at separating clusters at high density. And the disadvantages is that it does not work with the varying clusters of density with high dimensions. That's all we have today. Thank you very much.
Hello all, I am Dikshit Reddy Tineti. I belong to Group 9 in the KDD project. Now I'm going to speak about the topic agglomerative clustering. First, let's see what is an agglomerative approach briefly. It is shortly known as HSC, which means hierarchical agglomerative clustering. It is a most common type of hierarchical clustering, and this is used for grouping the objects in clusters based on the similarity. Also, this is a basic principle rule behind this. It is also known as AGNES, which stands for agglomerative nesting. So basically here we start by assuming each data object given in the data as an individual cluster. So if we see this picture, let's consider these individual objects as a single cluster. And let's say this cluster and this cluster are similar. And in the next step, we merge these two clusters into a single cluster, which is FG. So this process continues until there is only a single cluster which has all the objects in it. So basically, the agglomerative approach is a bottom-up approach. Now let's deep dive into the concept of agglomerative approach with an example. We follow the same bottom-up approach in this. We start by um, assuming each individual object as a single cluster. So here A, B, C, D, and E are considered as an individual objects in this step. At step 0, let's say we have n as an number of clusters. So as we have 5 clusters, the value of n is 5. At step 1, we merge the clusters which are close to each other. Let's say A and B are close to each other. So we merge these individual clusters into a single cluster, which is AB. Now we need not consider the individual clusters A and B. So we discard these two individual clusters. So the n value becomes 4, which are A, B, C, D, and E. In the next step, we merge object D and object E as they are close to each other. So this forms DE as a single cluster. So in the next step, we merge C with the cluster DE into a single cluster CDE. In the last step, we are only left with the cluster AB and CDE. So we merge these two clusters in to form a single cluster with all the data objects. So this is how agglomerative approach works. The same is written in the words here. At the start, each object is a cluster, and from then we merge two clusters which are most similar to each other until all the objects are merged into a single cluster. So the basic criteria which says two clusters are similar can be either a Euclidean distance or the similarity measure. There are some limitations too in this approach. It requires large number of large storage, which makes the computation process a little complex, and the algorithm are 4 times the size of k-means algorithm. As merging cannot be reversed, it creates some mess when the data is to be pre-processed. That's it.
Clustering is an unsupervised machine learning technique that divides the population into different clusters such that the data points in the same cluster are more similar and the data points in different clusters are not so similar. They are dissimilar. Points in the same cluster are very close to each other, whereas the points in the different clusters are far apart. Let's talk about the two types of hierarchical clustering methods. The first is divisive clustering and the other is agglomerative clustering. I'm going to talk about divisive clustering. It is a top-down clustering approach where the points in the dataset belong to one cluster and the split is performed recursively as one move down the hierarchy. There are some steps for divisive clustering. They are first, all the points in the dataset belong to one single cluster. Then the partition is performed in the cluster, and it is divided into two least similar clusters. We then proceed recursively to form new clusters until the desired number of clusters are obtained. Here we have three images, where the first image shows that all the data points belong to one single cluster. The second image shows that one cluster is separated from the previous single cluster, whereas the third image shows that further one more cluster is separated from the previous set of clusters. As we've seen in the sample dataset, we've observed that there are three clusters that are far separated from each other. So we stopped after getting three clusters. If we start separating further more clusters, we get this result.
Hello and good morning everyone. I'm Karthik Soma, here to discuss about the working of hierarchical clustering. Let's begin with what actually clustering is. Clustering is usually grouping of two individual identities which have the most common and similar properties in similar properties. And what is hierarchical clustering and how it works? Hierarchical clustering usually starts by treating each observation as a separate cluster. Then what it does is it repeatedly executes two basic steps, which are nothing but identifying clusters that are closely together or have close similarities between each other. And then the second step is that these clusters with the most similarities within them are merged together. This iterative process continues until all the clusters are merged together into to form a single whole board cluster. Now let's look at the diagrammatic representation. As we can see in the first box, there are two clusters which are identical or similar to each other, which are merged together. And in the third box, as we can see, two clusters are again identified and they are merged into one in the fourth diagram. In the similar process, the clusters are merged together having similar properties, which in the end we can see that as forming a whole single cluster body. What exactly is the relationship between the clusters is that the main output of hierarchical clustering is a dendrogram, which shows the hierarchical relationship between the clusters. Now let's move on to the implementation part. So let's consider that we have a few name points on a 2D plane with the x and y coordinates. Each data point can be considered as a cluster of its own, cluster of its own. Now we want to determine a way to compute the distance between each of these points. For this, let's try to find one thing we can do is we can try to find the shortest distance between any two data points to form a cluster. So once we find the least distance between these so-called data points, we can start grouping them together and form a cluster of multiple points. These we can as shown can be represented in a tree-like structure called a dendrogram. As a result we have three identical groups which are formed from the initial six data points. We can name them as P1 P2 as one group, P3 P4 as another group, and P5 P6 as a third group. So similarly we will get three dendrograms. In the next step, we try to bring out of these three groups, we try to bring the two groups which are most similar to each other into another dendrogram. For example, let's say P3 P4 and P5 P6. These two groups are similar to each other, can be brought under one dendrogram because they are closer together than when compared to the P1 P2 group, which can be shown as shown and seen in the below pictures. Then we finish, and that is when we are left with one cluster family and finally bring everything together. We can see how the cluster on the right went to the top with the gray hierarchical box connecting all of them together. So that's how exactly how the implementation for the hierarchical clustering works and the grouping takes place. So that's what hierarchical clustering is all about. So if at all you have any doubts, you can reach out to me on my personal email ID. So thank you for giving me this opportunity. Have a nice day.
Hello all, my name is Shalom Satvik Tatapudi, and I belong to Group 9 in the subject KDD. So this is part of our project presentation, and these are my 5 slides that gives the detail about measures of cluster validity. So there are numerical measures that are applied to judge various aspects of cluster validity, and they are classified into the following types. So as you can see in the slides, there are 2 types of measures. One is internal measure. In internal measure, we use to measure the goodness of a clustering structure without respect to external information. The examples are, the sum of squared error method and cohesion and separation and Silhouette quotient. And the other method of measure that we use for cluster validity is external measures. There are several measures like entropy, purity, precision, which are commonly used to evaluate the performance of classification model. But in these slides, I'll be discussing about entropy and purity. Let's move to the next slide. Here we have the SSE. In SSE, the clusters in more complicated figures are not well separated, and the internal index used to measure the goodness of a clustering structure without respect to the external information. SSE is very good comparing in two clusterings or two clusters, and it can also be used to estimate the number of clusters. And let's move to the next slide, which is cohesion and separation. So cluster cohesion measures how closely the data or the related are objects in a cluster, and cluster separation measure how distinct or well separated a cluster is from other clusters. So example is the squared error. So cohesion is measured by within cluster with sum of squares, as you can see the formula, and separation is measured by between the sum of squares. You can see the formula where Ci is size of cluster I. And a proximity graph based approach can also be used for cohesion and separation. Cluster cohesion is sum of the weight of all links within a cluster. Cluster separation is sum of weights between the nodes in the cluster and nodes outside the cluster. Let's move to the other measure that we have is Silhouette quotient. Silhouette quotient combine ideas of both cohesion and separation, but for individual points as well as clusters and clusterings. For an individual point I, for example, you can see the figure that is given. Calculate A, this average distance of I to the points in its cluster, and calculate B is equal to the min of average distance of I to point in other cluster. The Silhouette quotient for a point is given by S is equal to 1 minus A by B if A is less than B. So typically between 0 and 1, the closer to 1, the better. So it can be calculated by average Silhouette with width for a cluster or a clustering. And next move to the external measures of cluster validity. So here we have a k-means clustering results for LA document set, and so the entropy is for each cluster the class distribution of a data is calculated first. For cluster J, we compute Pij, the probability, and the member of cluster J belongs to class I as follows. And the purity is defined using the terminology derived for entropy. The purity of cluster J is given by purity is equal to max Pij, and the overall purity of a clustering by purity, and the formula is given. So final comment I would give of the cluster validity is the validation of clustering structures is the most difficult and frustrating part of cluster analysis. Without a strong effort in this direction, cluster analysis will remain a back art, accessible only to the true believers who have experience and get courage. Well, thank you for giving this time, and
Hello everyone, I'm Divyaja Reddy Divedi, who belongs to Group 9. As a part of project presentation, I would like to talk about strengths of hierarchical clustering, its space and time complexities, and its limitations. Um, so the first slide is about strengths of hierarchical clustering. We can form clusters of any shape, and there is no restriction on the shape of the cluster. In the k-means or partitioning clusters, we need to set out predefine the k value. For example, if the k value is 4, then only 4 clusters will be formed. But in hierarchical approach, there is no need to define the k value in advance, and we can complete the whole process with the dendrogram, and after the completion of the process, we can vary the k value to whichever level we want. So the desired number of clusters need not to be known or need not to be predefined. Depending on the level we are cutting the dendrogram, we can change the number of clusters as per our choice. Um, in k-means, like if the k value is 3, then only 3 clusters will be formed. But in the hierarchical clustering, once we get the dendrogram, if we want 3 clusters, then we only have to change the cutting of the tree. If we want different number of clusters, we only have to retain the process to find the number of clusters. These hierarchical clusterings correspond to meaningful taxonomies like in biological sciences for animal kingdom, phylogeny reconstruction, and in web for product catalogs, etc. So these are the advantages or strengths of hierarchical clustering. And coming to the space and time complexities, or the space complexity for hierarchical algorithms is order of n square. This is because of the space required to store the adjacency or similarity matrix. This similarity matrix stores the distance of every pair of elementa, and the space required for a hierarchical clustering algorithm is very high when the number of data points are high. Coming to the space complexity of dendrogram, the space complexity for it is order of k into n, which is much less than the order of n square. The time complexity will be order of n cube, because we need to perform n iterations, and in each iteration we need to update the similarity matrix and restore the matrix. So the time complexity is also very high. This time complexity can be reduced to order of n square into log of n by using some approaches of data structures. And finally, coming to the limitations of hierarchical clustering, once a decision is made to combine 2 clusters, it cannot be undone. The objective function cannot be directly minimized, and there is no mathematical objective for hierarchical clustering. It has high space and time complexity, and hence this clustering algorithm cannot be used for huge data. Thank you.